We can learn nucleophilic aromatic substitution. We have learned about nucleophilic aliphatic substitution, that is the SN1 and SN2 mechanisms, kinetics, stereochemistry, etc. We have learned the chapter alkyl halides. So alkyl halides undergo nucleophilic aliphatic substitution where the halide ion is replaced and substituted with any other nucleophile like OH minus, etc. So do you remember whether this methyl chloride it is converted to methanol when it is treated with alcoholic potassium hydroxide. So here this is the aromatic nucleophilic substitution. So here the substrate is aryl halides. In nucleophilic aliphatic substitution the substrate is alkyl halides. Here it is aryl halides like chlorobenzene, bromobenzene, etc. But unlike alkyl halides, aryl halides are less reactive towards this nucleophilic aromatic substitution. So you know that aryl halides are compounds containing halogen directly attached to an aromatic ring. They have the general formula ARX. And I told that aryl halides are comparatively unreactive towards nucleophilic substitution reactions. But no, they can even undergo nucleophilic substitution reaction where the halogen atom of this aryl halide can be replaced and substituted with the other nucleophiles. So for this reaction to happen, there should be certain conditions. There are certain conditions. That means first one is there must be the presence of certain groups at certain positions. So we can discuss much about this in the coming slides. The first point is delocalization of electrons by resonance. We know that halobenzenes or chlorobenzene, it has a benzene ring. So obviously it can exist as a resonance hybrid of two Kekulé structures. And moreover, this chlorobenzene, it can even exist in three more structures. Chlorine has the tendency to donate more than a pair of electrons to benzene ring by its resonance effect, and it forms a double bond with the benzene ring, and as a result, as the chlorine atom is donating one more pair of electrons to benzene ring, these electrons will be appearing at the ortho and para positions, and para position of this carbon atom to which the chlorine is attached. So totally there may be 5 different structures for chlorobenzene. So the chlorobenzene actually it is a hybrid of 5 different structures. We know that if the number of contributing structures is more, the stability of the hybrid will be high. So the chlorobenzene or the aryl halide will be highly stable because of the contribution from these 5 different structures, and stable compounds are less reactive. So that is the first explanation for the low reactivity of aryl halides, that is due to the high stability of aryl halides due to delocalization of electrons by resonance. So as mentioned in the previous slide, aryl halides are less reactive towards nucleophilic substitution. So is the vinyl halides. Vinyl halides are also less reactive towards nucleophilic substitution. So that means aryl and vinyl halides, they have very low reactivity towards the usual nucleophilic reagents. For example, if we heat this bromobenzene or the vinyl bromide with alcoholic silver nitrate for days, there won't be any formation of silver bromide. That means the bromine atom from the bromobenzene or from the vinyl bromide, that is not at all replaced. That means that reaction does not happen. So why it is so? We have to learn much about the structure of aryl and vinyl halides to understand why these two species, these two chemical entities like aryl halides and vinyl halides, why they are less reactive towards nucleophilic substitution reaction. So we have to see the structure of aryl and vinyl halides. The low reactivity of aryl and vinyl halides towards this nucleophilic substitution may be due to the following different factors. First one is delocalization of electrons by resonance, that we can see why it happens, and the difference in sigma bond energies due to differences in hybridization of carbon. And the third one is carbon halogen bonds of aryl and vinyl halides are unusually short. So we have to explain much about each of these points. In the previous slide we have seen 5 different structures for chlorobenzene, and out of these the structure 3, 4 and 5, the chlorine bears a positive charge and the ortho and para positions of the ring bears a negative charge, and the contribution from the structure 3, 4 and 5 stabilizes the chlorobenzene, and it gives a double bond character to the carbon chlorine bond. So carbon and chlorine are thus held together by double bond. It is held together more than a single pair of electrons, and the carbon chlorine bond is a stronger bond. So these points and all I explained in the previous slide itself. Similar is the case with vinyl chloride. Vinyl chloride is also, it is a hybrid of two different structures. Vinyl chloride is actually, the structure is CH2 double bond CHCl. So this is the structure 6, that is the normal structure of vinyl chloride. Here also the chlorine has the tendency to share more than a pair of electrons with the carbon atom, so that results in the formation of a double bond between carbon and chlorine in the second structure, that is structure number 7. So as a result, chlorine has a positive charge and the negative charge is developed at the second carbon atom. Anyway, the vinyl chloride, it is a hybrid of two different structures, the first structure and second structure. Here it is numbered as structures 6 and 7. So as a result, vinyl chloride is also, it is more stable than other chlorides like alkyl chlorides. And moreover, and there is a carbon chlorine double bond formation. There is double bond between carbon and chlorine atom. You know that the double bond, it is a stronger bond. So for the substitution reaction to occur, anyway the carbon chlorine bond has to be broken. So as there is a double bond character between carbon and chlorine, it is little difficult to break this chlorine atom. So it is very difficult for this vinyl chloride also to undergo the substitution reaction. The third point says about the bond length. The carbon halogen bonds of aryl and vinyl halides are unusually short. In chlorobenzene and vinyl chloride, the carbon chlorine bond length is only 1.69 angstrom, and in alkyl halides it is 1.77 to 1.80 angstrom. So this is because the carbon halogen bond in aryl and vinyl halides, it has double bond character. So it is a shorter bond, and in alkyl halides it is a single bond. So double bond is a shorter bond. Whenever the bond length is short, the strength of that bond will be high. So this is the third reason for the low reactivity of aryl and vinyl halides. Even if the aryl halides, they are less reactive towards this nucleophilic substitution reaction, they can also undergo this substitution reaction under certain conditions as mentioned in the first slide. So based on the conditions that are applied, it may take up any of the following mechanisms. First one is bimolecular displacement mechanism for activated aryl halides. Second one is elimination addition mechanism, which involves the intermediate called benzene. So we have to learn much about, or we have to learn in detail about both these mechanisms, why it is so, why that particular name, what is activated aryl halides, etc. So in the coming slides we can see more about it. So we can see what is bimolecular displacement. So as mentioned in the previous slides, aryl halides are less reactive towards nucleophilic reagents. However, the presence of certain groups at certain positions of the ring activates the halogen of aryl halides towards displacement. We have to see what are the groups and what are the positions in the coming slides. Electron withdrawing groups like nitro group, NCH3 thrice group, cyno group, carboxylic acid group, aldehyde group, keto group, sulfonic acid group, etc. have been found to activate the halogen located ortho or para to them towards nucleophilic aromatic substitution reaction. And electron releasing groups, they deactivate halogen located ortho and para to them towards nucleophilic aromatic substitution reaction. So we can see it is just the reverse of what we have learned in the electrophilic aromatic substitution reaction. So this is nucleophilic aromatic substitution. We have learned electrophilic aromatic substitution previously. In electrophilic aromatic substitution reaction, electron releasing groups, they were activating. But in nucleophilic aromatic substitution reaction, electron withdrawing groups are activating groups. And the degree of deactivation depends on how strongly they release electrons. In the case of electron releasing groups, in NH2 and OH group, they deactivate strongly. OR group, it deactivates moderately. The alkyde ion, they deactivate weakly. So here in this example, we can see there is para-chloronitrobenzene. There is an electron withdrawing NO2 group para to the chlorine atom. So the NO2 group, it is being an electron withdrawing group, that is an activating group. So this para-chloronitrobenzene can undergo nucleophilic aromatic substitution reaction where the chlorine atom that is replaced and substituted with the OH group. When you treat this para-chloronitrobenzene with 15% sodium hydroxide and when you heat it up to 160 degrees Celsius. So on the other hand, if we simply try to heat this chlorobenzene with the sodium hydroxide, this reaction will not happen. So for this reaction to occur, there should be the presence of an electron withdrawing group at the either at the ortho position or at the para position. Here in this example, there is an NO2 group at the para position. That means it is an electron withdrawing group and it activated this chlorobenzene towards this substitution reaction. That is why we got this para-nitrophenol. Simple conversion of chlorobenzene to phenol, that may not be possible under this condition. Understood? As the number of ortho and para-nitro groups on the ring increases, the reactivity also increases. The phenol is obtained from 2,4-dinitrochlorobenzene by treatment with the hot aqueous sodium carbonate and from 2,4,6-trinitrochlorobenzene by simple treatment with the water. We can see in the next slide. See these examples. First one is 2,4-dinitrochlorobenzene. So there are two nitro groups, one at one ortho position and the second one at the para position. So it is little more activated than the para-chloronitrobenzene that we have seen in the previous reaction. Here, as there are two nitro groups, if we simply boil it with aqueous sodium carbonate at temperature of 130 degrees Celsius, the Cl can be replaced with the OH group and you will get 2,4-dinitrophenol. The severity of the condition required for the replacement is reduced. And see the second example, it is 2,4,6-trinitrochlorobenzene. That means three nitro groups are present, all the positions, that is two ortho positions and para position. That is substituted with the electron withdrawing nitro group, and this particular 2,4,6-trinitrochlorobenzene is highly activated towards this nucleophilic substitution reaction, such that if you simply warm this compound with water, the chlorine can be replaced and substituted with the OH group and you will get 2,4,6-trinitrophenolpicric acid that we have synthesized in our lab. See, the severity of the condition has been reduced to a much greater significant amount. As I told earlier, in nucleophilic aromatic substitution, electron withdrawal causes activation and electron release causes deactivation. In electrophilic aromatic substitution, exact opposite effect is caused by electron release and electron withdrawal. So the mechanism of bimolecular displacement reaction. It has two steps. Here the example is shown for chlorobenzene. The first step is a slow step, that is the formation of carbanion 1. So the carbanion is formed by the attack of the nucleophile Z minus on chlorobenzene. And once this carbanion is formed, from this carbanion the chlorine leaves as chloride ion and you will get the product C6H5Z. So ultimately what happens, the aryl chloride C6-chlorobenzene C6H5Cl is converted to C6H5Z by a two-step mechanism. First step is the slow step, rate determining step, that is the formation of carbanion. Second step, from this carbanion the negatively charged chlorine, the chlorine is leaving us chloride ion and you will get C6H5Z. The intermediate formed in the first step of bimolecular displacement reaction, it is a carbanion. Actually, this carbanion is a hybrid of three different structures where the negative charge can be seen located at the ortho positions and para position, because the Z, the nucleophile, it is approaching this benzene ring with a negative charge, with a pair of electrons. So whenever this Z, whenever it forms a bond with this benzene ring, it is sharing that pair of electron to benzene ring. So two electrons will be made free and these electrons will be seen present or located at the ortho positions and para position. That is why we have three structures for this carbanion, and we can represent this carbanion as a hybrid of these three structures, having a negative charge to be shown in the center of this halfly formed circle. This broken circle indicates that one double bond is not there. It is broken and the electrons are seen delocalized. Delocalized means that electrons may be present at the ortho positions or the para position. So in nucleophilic aromatic substitution, the intermediate is an actual compound, a structure like 5, it is shown below, containing a tetrahedral carbon and having the negative charge distributed about the ring. It is a comparatively stable structure. These points and all I have discussed in the previous slides. That is, in nucleophilic aromatic substitution, the first step is the formation of the carbanion, and it determines the overall rate of the reaction, and once formed the carbanion rapidly reacts to yield the final product. And difference in the rate of formation of carbanion, it is determined by differences in the stability of the transition state. Factors that stabilize the carbanion by dispersing the negative charge stabilize the incipient carbanion of the transition state. So you know that any factor that can disperse the charge, whether it may be positive or negative depending upon the reactions. So here in this case it is carbanion that is formed, negatively charged carbanion. So any factor that can disperse this negative charge may stabilize this carbanion. So in the case of chlorobenzene, you can see this is before the formation of the carbanion there is a transition state developing a negative. In the transition state there is a negative charge is developed, it is getting developed. So any factor that can disperse this negative charge, that may stabilize this transition state, that may ultimately lead to the stabilization of the carbanion. We know that electron withdrawing group that may disperse the negative charge of the transition state leading to the carbanion formation and that of the carbanion, and electron releasing group that may intensify the negative charge. Now we understood why it is said that the electron withdrawing groups are activating groups in this nucleophilic aromatic substitution reaction, because in nucleophilic aromatic substitution the intermediate it is actually a carbanion. Carbanion has a negative charge, so electron withdrawing group that can withdraw the electrons from this carbanion or from the incipient carbanion or from the transition state, leading to the dispersal of that negative charge and ultimately the stabilization of the carbanion. Electron releasing group on the other hand, they may be releasing electrons to the already negatively charged carbanion. So what happens to a negative charge? the negative charge will be getting intensified, isn't it? And as a result, the stability of that particular carbanion also will be less. That is why it is said that electron withdrawing groups are activating in nucleophilic aromatic substitution and electron releasing groups are deactivating. So that all depends upon the charge of the intermediate that is formed. Here the intermediate formed is negatively charged carbanion. This slide shows examples of electron withdrawing groups that withdraws the electrons from this carbanion, and that causes the dispersal of the negative charge and stabilization of the carbanion, and ultimately leads to the increased rate of reaction. The examples we have learned earlier: NCH3 thrice, NO2, CN, SOCH, COH, CHO, COR, etc. That is halide ions, etc. Here we can see that the electron releasing groups like NH2, OH, OR minus and R minus, etc. they releases the electrons and they intensifies the negative charge of the carbanion and decreases the rate of reaction of these aryl halides towards the substitution reaction. Now we have to see about the orientation in nucleophilic aromatic substitution reaction. For bimolecular displacement reaction to occur, the electron withdrawing group should be present at the ortho and para positions of the carbon to which the halogen is attached. Why it is specified? What is the reason for such a specification? So for that we have to see the structure of the carbanion formed from para-chloronitrobenzene and meta-chloronitrobenzene. So first is the case with the para-chloronitrobenzene. Here in this structure, the Z, the nucleophile, gets attached to the carbon to which chlorine is already attached, because in nucleophilic substitution the chlorine has to be replaced with the Z. So the CCl bond should break and Cl should leave the molecule, and at that place the Z should get attached. So in this particular example of para-chloronitrobenzene, when this Z gets attached to this para-chloronitrobenzene, what happens? There is the intermediate formation of carbanion, and as we all know, the carbanion it will develop negative charges at the ortho positions and the para positions. So in such a para attack, in this attack we can see the central structure, the negative charge is developed at the para position, and at the para position there is a nitro group, and this particular structure may be highly stable. Why it is so? The nitro group being electron withdrawing, even though this nitro group withdraws electrons from all the positions of that particular benzene ring, the electron withdrawal will be more effective from the carbon to which the nitro group is directly attached. So here in the central structure, the negative charge is developed on the carbon to which the nitro group is directly attached. So the electron withdrawal from that particular carbon will be more effective, and this second structure or the central structure is especially stable because negative charge is developed on the carbon bearing the substituent. So the intermediate carbanion formed by attack on this para-chloronitrobenzene or by the para attack is found to be more stable. The actual structure of this carbanion, it is a hybrid of all these three different structures, out of which one of the structure is especially stable. So that highly stable structure contributes to the stability of that intermediate or the hybrid carbanion also. Attack on the orthochloronitrobenzene also yields an especially stable carbanion. So in the structure, the reaction given as the second reaction, we can see that is the attack on the orthochloronitrobenzene. Here also the third structure, that means the ninth structure here. Just see, there is a negative charge on the carbon to which the NO2 group is attached. So this is an especially stable structure. So carbanion formed by attack on the ortho position, on the ortho isomer, ortho substituted chlorobenzene, that is also found to be highly stable, that promotes the reaction. But see the case with the first example, the example for this meta attack, see, meta-chloronitrobenzene, is there any structure where the negative charge is developed on the carbon to which this nitro group is directly attached? No. So we can say that there is no especially stable structure in the case of meta attack. So such a stable structure is possible only for para and ortho attack. That means we can say that the electron withdrawing group should be present either at the either at the ortho position or para position, or at ortho and para positions. If the electron withdrawing group is present at the meta position, that may not lead to the formation of a stable carbanion. So in the beginning I have mentioned that this nucleophilic aromatic substitution reaction may happen either by bimolecular displacement mechanism or by elimination addition mechanism. If there are electron withdrawing groups present either at the ortho or para positions or both at the ortho and para positions, it may take up this bimolecular displacement mechanism. So if the electron withdrawing groups are absent, this nucleophilic aromatic substitution reaction can be made possible by using very stronger bases and at very high temperature. So this substitution that takes place by this mechanism is called Benzene mechanism or elimination addition mechanism. For this elimination addition mechanism to happen, there should be the presence of, we must use a very strong base as well as we have to apply very high temperature. So the mechanism, that is second mechanism, is called benzene. It is not benzene, it is benzene mechanism or elimination addition mechanism. The structure of benzene, there is an additional bond between two carbon atoms by sideways overlap of sp2 orbitals. We can see an additional bond that is formed by sideways overlap of sp2 orbitals. The new bond orbital that is formed by sideways overlap of this sp2 orbitals that lies along the side of the ring, it will not interact with the pi electron cloud lying above and below the plane of the ring in benzene ring. And this sideways overlap is it is not a very strong bond. The new bond is a weak bond, and it is a benzene is a highly reactive molecule. So we can explain this mechanism by taking the example where this aryl halide it is converted to aniline. So here the chlorobenzene it is treated with a very strongly basic amide ion in liquid ammonia. Amide ion in a liquid ammonia, it is converted to aniline where the X is replaced with a NH2 group. And the reaction it involves two stages. First one is elimination stage and second is addition stage. That is why we call it as elimination addition mechanism. And the intermediate formed is benzene, as we mentioned in the previous slide. So benzene is formed in the elimination stage, and this elimination stage itself involves two steps. You can see the first step is abstraction of a hydrogen ion by the amide ion to form ammonia and carbanion 1. Here there is amide ion NH2 minus. It abstracts a hydrogen as proton. From where? From the ortho position of the carbon to which the halogen is attached. So this NH2 minus abstracts an H plus. It abstracts an H plus and NH2 minus is converted to NH3 ammonia. And this carbon, the carbon from which the hydrogen is abstracted as H plus, it is now surrounded by a pair of electrons, and that particular carbon is having a negative charge. This is the first step of elimination reaction. Elimination stage has two steps. So the second step of elimination is that the carbanion 1 formed in the first step, it loses the halide ion to form the benzene. See, the carbanion formed that loses that halogen, the halogen that is leaving us X minus, that is by taking its electron pair, and this drawing shows a clear narration. So this X is leaving us X minus. Now at the ortho position there is a carbon with a lone pair of electrons. So that carbon shares that electron with the carbon from which the X is leaving. That leads to the formation of benzene. And addition step. So by this elimination step is over. Addition step also involves two steps. First step is attachment of the amide ion to form the carbanion 2. So in the second step of elimination stage, there is a formation of benzene, and in the addition step what happens, the amide ion it is getting added to this benzene. For that addition, NH2 minus is bringing the electrons to form bond with the carbon atom. So whenever, as soon as this NH2 forms a bond with this carbon, that benzene, that one new bond was formed, during the formation of benzene. That particular bond breaks, and again that electrons goes back to the original carbon atom from which that electrons came for, it was donated for the formation of that additional bond. So there is the formation of a second carbanion 2, and from this to this second carbanion, from ammonia NH3 is formed in the first step. So from ammonia, one H plus is transferred, or it is added to this carbanion, and that is from the same carbon from which this NH2 minus abstracted this proton in the first step. So that proton again it is received by that carbon atom having this negative charge, and you will get aniline, and ammonia is converted to NH2 minus. Now we can make a comparison between nucleophilic aliphatic substitution and nucleophilic aromatic substitution. As we know, in nucleophilic aliphatic substitution there are two mechanisms, SN1 mechanism and SN2 mechanism. In nucleophilic aromatic substitution also two mechanisms are there, bimolecular displacement mechanism and benzene mechanism or elimination addition mechanism. In aliphatic nucleophilic substitution and in SN1 reaction, the leaving group leaves before the attacking reagent gets attached. That result in the formation of a carbocation, that is a two-step mechanism. And in SN2 reaction, the leaving group leaves at the same time as the attacking reagent gets detached. So, but in aromatic nucleophilic substitution, the departing group, the leaving group, the halide ion leaves after the attacking reagent is attached. And in SN1 reaction, a positive charge develops on the carbon during SN1 reaction, and there is no such charge during SN2 reaction. And in aromatic substitution, a negative charge is developed during the nucleophilic aromatic substitution. Just remember that carbanion, it is having negative charge. And the SN1 reaction is favored by electron release because there is an intermediate formation of positively charged carbocation, and SN2 reaction is not influenced by electronic factors because there is no particular charge on this intermediate. And the nucleophilic aromatic substitution is favored by electron withdrawal. See the comparison, the reaction mechanism it is shown here. In SN1 reaction, the first step is slow heterolysis of the carbon halogen bond forming the carbocation, and to this carbocation the conjugate base is added forming RZ. The positive charge develops on the carbon atom in SN1 reaction. And in SN2 reaction, the departing group departs and the leaving group also gets attached simultaneously. There is bond breaking and bond making that occurs simultaneously. And in nucleophilic aromatic substitution reaction, especially by bimolecular displacement mechanism, there is the intermediate formation of carbanion, and from this carbanion halogen leaves of halide ion. So with this we come to a conclusion of this particular chapter, nucleophilic aromatic substitution. And we have seen, actually we can just divide this particular chapter into three major sections. First one is that first part discusses with the low reactivity of aryl halides towards this nucleophilic substitution reaction. We have seen the reason for that. In the second part we have seen that there are two different mechanisms are there, a bimolecular displacement mechanism and elimination addition mechanism. And in bimolecular displacement mechanism we have seen the mechanism, its orientation and effect of substituents on this rate of reaction, etc. And as a third part we have seen this elimination addition mechanism or the Benzene mechanism. And towards the end, we just made a comparison between alkyl nucleophilic substitution and aromatic nucleophilic substitution. So with this chapter is over. I would like to mention my special appreciation and thanks to our dear Gautam Gopakumar for preparing such a beautiful PPT including all the points. Thank you, Gautam.